Hello and welcome to software architecture course. Today we will learn another architectural pattern called microkernel, and this particular pattern is a part of adaptable systems. So let's understand this particular pattern. This is a pretty old pattern. It has been proposed at least more than 20 years ago, and this particular pattern has been the foundation for operating system, science operating system. So basically this particular pattern is important from that perspective, how microkernel is used to build complex software like operating system, and how it is kind of relevant even today. So like other architectural patterns, microkernel architecture pattern can be also described as a three-part schema. We have already explained what is this three-part schema in the context of other patterns. So the first part is called the context. Context means that in which context this particular pattern, microkernel pattern, can be used. So the context here is that the development of several applications that basically use the similar programming interfaces, and that needs to build on the same core functionality. So the main important thing is that there are many applications that need to use the same kind of programming interfaces, and through these programming interfaces interacts with a core functionality. So there is a core functionality. There are several applications that need to interact with, and we are talking about this core functionality. Now, why do we need microkernel pattern? The problem is, or the requirement is, that the developing software for an application domain that basically needs to deal with a broad set of similar standards and technologies. So essentially we need to build a software for a particular application domain, and this software should be adaptable enough, which is why this kernel is called a part of adaptable systems. So essentially the main requirement is that there are broad set of standards and technologies, and this particular software that we are going to build needs to address those similar standards and technologies. And importantly, it is adaptable, because as and when the standards and technologies vary, of course within the similar spectrum, then the change that's required on this particular system should be minimal. In other words, it should support continuous evolution of the platform. It should be portable and adaptable. What that essentially means is, if you think that you are building, let us say, Unix kernel system, so this kernel should be designed in such a way that it can basically support various types of applications, device drivers. At the same time, it should be able to also be portable across different types of hardwares, as long as those hardware belong to the same family. So microkernel, so in the three-part schema, the first one is context, second part is a problem, third part is a solution. So solution is basically one need to encapsulate the set of fundamental services in a microkernel component. So in order to design a microkernel, one needs to basically identify what the set of fundamental services, and those services should be not only designed but also encapsulated, so that it basically is independent of more hardware dependent aspects. And the moment it becomes independent of hardware dependent aspects, then it becomes easy for other components to interact with in a microkernel through well-defined APIs. And another important part is microkernel. The size of microkernel should really be small. It shouldn't really be a big system. It's a small system, at the same time it's a very portable and adaptable system. So the various components of microkernel can be described using these concentric circles, where the microkernel is in the center, and around microkernel there are a set of internal servers. On top of internal servers there are external servers. On top of external servers there are adapters, and client basically is completely shielded from microkernel. Client basically interacts with the adapter then interacts with the external servers, and external server then interacts with either internal server or microkernel directly. So with this set of concentric circles, we have already introduced what are the important components of microkernel. So let's start with internal server. What is the purpose of internal server? Basically, internal server implements additional services that are not part of microkernel. Now, typically these additional services are different types of device drivers. If you are implementing the microkernel in the context of operating system. So if you are building an operating system and you are building the kernel, then you can adopt this microkernel pattern. In that case, you completely separate the device drivers from the kernel. That's called internal servers. Essentially, internal servers are additional services which are typically device drivers, which can either run as a process or it can be a shared library. Then another set of components are called external servers. External servers are essentially more complex. These are functionalities that are required for the clients. They typically don't run, or they typically don't exist as a shared library. They are basically independent processes. External servers are also not directly exposed to the clients. It is through the adapters through which the client basically interacts with the system. Clients are of course the client programs. So, microkernel in all this essentially will have the core functionality, the communication mechanism, and microkernel would directly interact with the internal servers. So let's look at the microkernel component in detail, or microkernel pattern in detail. So the main component of this pattern, which is the microkernel, should be, as I said, it should be small in size and it should be optimized for memory. Why it is small in size? Because this is the core of the computing system. Microkernel pattern is typically used, as I said earlier, to build operating systems, and the operating system must run all the time. So even if other parts, different device drivers or external systems, external servers, even if they fail, the kernel part should not really fail. And one of the main design principle for that is that it should be optimized for memory. It should be really lightweight and have a very small memory footprint, and should provide the core mechanisms. Hardware dependent parts should be actually encapsulated. Microkernel really should not expose any hardware dependent part. So what that means is that different hardware dependent parts should be encapsulated, and appropriate set of APIs, appropriate set of modules should be there through which hardware dependent parts should be accessed. So system resources are typically modeled inside microkernel. Examples are process files. So the notion of a process, managing process, process page tables, file handling, these are core part of the microkernel pattern. So the way microkernel exposes this services to internal servers, or the way it interacts with internal servers, is basically through a set of atomic services. Now these are also called mechanisms in microkernel parlance, and by composing these atomic set of services, more complex functionality can be built. Now in the OS design, typically microkernel runs in a privileged mode, meaning that because the microkernel is directly dealing with the hardware, so microkernel would run in a privileged mode, and everything else, meaning the internal servers, external server, they all run in a user mode. Now, what is user mode and privilege mode? These basically are very specific to the hardware. Nowadays, most of the modern CPUs, Intel-based CPUs, basically support set of instructions which can be executed by only privileged mode software component. So, and there are other instructions which are basically can be executed by any other application. So essentially, in order to, let's say, execute instructions like popping the status register, changing the page table. So these are CPU instructions, memory management instructions. So these instructions are called privileged instructions, and only microkernel is allowed to access or use those instructions. However, there are other instructions, for example, adding two numbers or moving data from memory to the register, normal registers, doing arithmetic operations, function call. Those things are essentially user mode, and any other component can actually use it. Now let's look at this class diagram for microkernel. Microkernel has a set of methods, and microkernel in this example is interacting with other components. So microkernel has a method called execute mechanism. So we said that each atomic service essentially is called mechanism. So execute mechanism is going to execute a particular mechanism, start the communication, which is init communication, then find the receiver, create the handle, for example, create a file handle, sending messages, calling internal server, execute mechanisms. These are the methods that are basically be present in microkernel. So when I'm basically saying that these are methods, these are high level methods. Of course, these are really not the methods that, or these are not the only methods that you are going to implement if you are looking at a real microkernel. So the methods that I'm showing here are basically an indicative set of functionality that are required. It's again a pattern, it's a high level solution. So don't assume that these are the only methods that are present, but these methods are there to indicate the kind of functionality, responsibility that microkernel needs to perform. So microkernel basically activates one or more internal servers. Microkernel calls an external server, and external server essentially performs receive request, dispatch request, execute a set of a particular service. Now the client client has a method called do task that in turn interacts with this adapter. This adapter is in turn interacting with the external server as well as it is interacting with the microkernel. So let's look at the role of a server. We have two types of server, internal server or as well as the external server. So let's look at what is internal server. It is also known as a subsystem. So as I said earlier, it basically extends the functionality. One good example is having device drivers, additional device drivers. So microkernel essentially invokes the services based on different client requests. Example is that if you are connecting a USB device, a camera let us say, and then there is a driver that handles this camera, microkernel would invoke the services which are present in the internal server, which is again dealing camera. It is adaptable system because when somebody has written microkernel, that person has got, or that group obviously has no idea that eventually microkernel is going to interact with, let's say, camera device. That way it becomes extensible. So internal servers can be considered as extensions. External servers are essentially also known as personalities. So it basically gives its own view. It creates a new view on top of the microkernel. These are typically used to basically give different flavors of different types of OS. So the experiments were performed when the research group who has proposed microkernel. So what they showed is that one can build a microkernel, and then on top of that it is possible to give different flavors of different operating system. For example, on the top of this simple microkernel you can create a OS2 flavor, or on the top of a particular microkernel one can build a Mac operating system. So these are the two examples that were demonstrated to show what an external server is. Now different servers, obviously they're going to implement different policies for a specific application domain. The policies that are there for Mac operating system is not going to be same as OS2, and these policies are defined and implemented inside the external server. So what does it do? It basically performs service requests which are coming from the client via the adapter, and then it performs those requests. So the way it performs the request is it basically interprets the request, and then it executes the appropriate services. For that it might take a help of internal server, and then it returns the result to the client. What does the client do? Client basically is an application, the end user application. It is associated with exactly one external server. It is not associated with multiple external servers. So if an external server is an Mac OS, then the client would be an application written for Mac OS. Now that obviously means that client really does not interact with the kernel directly. It interacts only through the adapter. It accesses the services provided by the external service through the adapter. So adapter essentially protects the client from the implementation detail of the microkernel. It uses a communication mechanism provided by microkernel for interaction, and it receives the service request from the client. It forwards a call to the appropriate server. By appropriate server it means that it can forward the call either to the external server, or it can forward the call to the microclient, to the like microkernel, and invoke methods of external servers on behalf of the client. So very important that the client makes a call and adapter receives it, then invokes appropriate method of the external server, and then sends the result back to the client. That's what it's meant by it invokes method on behalf of a client. So adapter basically stands in between the client and the external server. Microkernel can be also represented as a layered architecture. So here is this example where there is a microkernel. Microkernel is extended with a set of internal servers. Then this microkernel plus this internal server, that's the whole system, and external servers are essentially the flavors which are on top of microkernel. Adapter is basically shielding these external servers, and these applications are interacting through this adapter. Let's look at this sequence diagram to understand what happens. So client calls for a service. Client calls for a service to the adapter. Adapter in turn creates a particular request, and then it basically invokes the microkernel to start a communication mechanism. Now microkernel basically in response to the communication, it finds the appropriate external server handle and then essentially returns the address to the external server to adapter. Adapter then makes a typically RPC call, a remote procedure call, to the external server. External server in turn executes the service, sends the result back to adapter, and adapter then sends the result back to the client. Now this particular sequence diagram is an extension of the previous diagram, where one can have more complex operations. So external server, when it receives a request from the adapter, it can execute and send it back, or it can again call microkernel, and microkernel then calls the adapter, calls the internal server, because the functionality that external server is requesting, that cannot be provided by microkernel directly. Therefore, a microkernel essentially takes the help of internal server, and internal server, when it executes the service, sends the result back. Microkernel would return the response as well as the value back to the external server, and then external server again sends it back to the adapter. Example could be that suppose you have the camera, and then from the client application, basically download lectures from the camera to the hard disk. Then this internal server will be responsible for accessing the camera and then downloading the pictures from the camera to the system's hard disk. Now this particular method will be invoked by microkernel. So they say that internal server essentially serves as an extended functionality, extended feature, kind of a plugin, and internal server can be a separate process or it can be a shared library. So let's look at microkernel in a more detailed manner, specifically how it can be implemented. These are the set of steps that one need to perform to implement a microkernel. First one is analyze the application domain. Second one is analyze the external servers. Then categorize the servers, partition those categories of functionality that are required. Then find a consistent and complete set of operations and abstractions. This is basically a pretty complex design task. Then determine the strategies for request transmission and request retrieval. Structure the microkernel component. Specify what kind of API that would be required for the microkernel. Then microkernel, as you know, microkernel is responsible for all system resources. This particular step number 9, would be essentially to understand how it can manage the system resources, design and implement a set of internal servers, then implement the external servers, implement the adapters, and then finally develop client application. These are the different steps. If you are only focusing on microkernel, then of course step number 10, 11, and 12 is not required. But nowadays microkernel comes with at least a set of basic internal servers and maybe a default external server, so you can't just skip 10 and 11. But at least the microkernel design ends at step number 9. So let's understand the client requirement now. As a part of client requirement, the first step is to analyze the application domain, which identifies what are the functionality that's required for microkernel. Perform the functionality analysis to identify different policies the external server requires to offer for the application domain. This is more of gathering requirement. Then next step is to analyze the external server that need to be implemented. So obviously while analyzing the application domain, it is necessary to identify the policies that external server need to offer, and then when in the second step, those policies that have been identified are now deeply analyzed, and what's identified is essentially the high-level interfaces that are required and the list of services and service categories. Very important, because external server is a complex piece of software. It may have many set of APIs, many set of services. They need to be grouped, they need to be categorized carefully, and these grouping of services are basically determined, controlled by the set of policies that are identified while analyzing the application domain. Then the next set of activities are categorization of the core services. Identify the core service functionality, and then, as I said, group them into a set of semantically independent categories. Example, group a set of functionality which are useful for memory management, group a set of functionality that are required for process management, group a set of functionality for low-level I/O, communication, and so on. Then identify the categories which are not directly related to application domain. For example, and which are quite general, like file system management, maybe memory management. These are not really directly related to the application domain. So in this case, the main focus is to build the system infrastructure. So after having those categories identified, like memory management, I/O, process, and so on, here I have just shown only a few set of examples. After identifying those categories, the next step is to decide which set of categories belong to the microkernel and which set of categories belong to the internal servers. So one of the heuristics, one of the rules that you can use is use the concept of frequency of use. So essentially, the categories of services which are close to the hardware or hardware dependent or very frequently used, these are basically part of microkernel. Like obviously the memory management should be the part of microkernel because this is the most frequently used component. But page fault handling, different drivers, file system, they can be part of internal servers. Next step is the core service design. Identify the operations for each category. So we have identified the categories and services. Now we go further deep and then identify what are the precise set of operations that are required for each category, and they're consistent as well as complete. Microkernel provides mechanisms for the policies of external servers. Remember that in the first step we said that the policies first need to be identified and then analyzed, which will then be used to basically design the external server. Now each policy that we identified, basically each policy is implemented through a use of different services that microkernel actually offers. So microkernel is going to offer a set of services, and using those services a policy will be implemented inside the external server. For example, the policies dealing with processes and threads, how to create, how to terminate, and how to schedule different processes and threads. This is a policy. Now this policy will be implemented by a set of services that microkernel offers, which are more atomic, more micro level services. So creation of process, the policies of creating process, creating threads, these will be implemented by using a set of microkernel services. Then determine the communication strategies, specify the facilities that microkernel should provide for communication between the components, like synchronous communication, asynchronous communication, one-to-one, one-to-many, or many-to-many communications. These are the different types of communication facilities that need to be decided. Again, this is completely dependent on the application domain. Then a set of core services, for example, message passing, shared memory based services, that need to be built first. Then, only then, other services can be built on top of those fundamental set of core services like message passing or shared memory based access. So the structure of the microkernel component basically separate the system specific part from system independent parts. This is an important segregation. Use a layer pattern inside the microkernel as well. For example, the lowermost one is the system specific components, uppermost will be system independent component, which will focus on different services which microkernel is finally going to expose to the external world. What kind of APIs will be there for microkernel? Decide how the interfaces should be available external. Microkernel can be a separate process, can be a separate shared library. Typically it is designed as a separate process. Modules are typically shared by other components. Microkernel module, if it is designed properly. So here the main quality of it that one needs to think about is having the low memory footprint so that it is efficient, and microkernel should not become a bottleneck. That's a very important part. Another important part is the resource management. Design microkernel resource management properly. Implement strategies for sharing resources, locking for exclusive use, allocation of resource, deallocation of resource. Maintain and inform the information about resource and allow access in a systematic way. And then design and implement internal servers. Separate processes or shared libraries centered around resources. Very important. Each internal server would be responsible for a particular type of resource. Active servers are typically implemented as processes which are always active, watching for events to arrive. So in that case, for example, the network resource handling, this could be an internal server, and this will always be live and watching the TCP ports or managing the TCP ports. There could be passive servers which are implemented as a shared library. For example, graphics card driver could be a shared library. A basic graphics card driver. Nowadays, of course, advanced graphics card driver are process as well. Page fault handler, for example, could be a separate process. So the basic graphics card driver could be a shared library, whereas page fault handler could be a separate process. Let's look at the client access component. External server is implemented as a separate process. It has its own service interface. Internal architecture obviously depends on the policies it comprises of, which is why the policies need to be defined at the beginning. Specify how external server is going to dispatch different requests to the internal procedures, how it's going to interact with the microkernel. These are important design decisions for external servers. Then finally, design the adapters. Decide the strategy. Is it one adapter for all the clients, or every client should have one adapter? These are the trade-off. Adapter need to really package all relevant information into a request and then forward the request to the appropriate external server. So there might be many micro level requests that comes from the client. It can group them, it can package them, and then can send it to the external server. This is important. So implementation of this adapter could be a proxy design pattern. There are different variants of microkernel system. It can microkernel system with direct client server connections. This is a variant. Another variant could be distributed microkernel system. Let's look at some more recent examples of microkernel. For example, this particular microkernel architecture that I have taken from Wikipedia. So the traditional BSD kernel for Unix was actually monolithic. Microkernel is more loosely coupled. So during the startup, the microkernel based systems require device drivers and many internal servers which are typically not part of the kernel. So which means that they are packaged with the kernel in the boot image, and the kernel supports a bootstrap protocol that defines how these drivers are allocated and they are actually started. Let's look at this particular diagram. So there is a hardware, and on top of the hardware there is this kernel. Kernel basically provides device drivers, dispatchers, schedulers, shared memory. So okay, so let's look at the one which is on the left. That's basically a kind of monolithic one, which has the device drivers and dispatchers, which is the traditional BSD kernels, and this has been modified now with a microkernel pattern. So the one that's on the left basically has this device drivers on top of that scheduler, on top of that IPC file systems, and then the application is on top of that. Whereas in the right hand side, this kernel has basic IPC mechanism, virtual memory management, scheduling, and everything else are set on top of this lightweight microkernel, like application, IPC, Unix servers, different device drivers. They all act as a plugin mechanism. Another example is basically more modern. This particular experimental effort was done at Microsoft Research Redmond more recently. So here Microsoft basically wanted to build a new type of OS called Singularity. So this Singularity OS basically is built using the microkernel architecture pattern. So the one on the right hand side, this particular indicates this microkernel. The rest are essentially those extensions. Here the Microsoft Singularity OS provides basic memory management, process creation, communication, scheduling, and I/O operations. Kernel calls only passes values. That's important. A process cannot really change the state of another process. That's what is a design decision taken while designing the Singularity operating system. So a code in Singularity OS is either verified by the compiler, or it is basically trusted code. So that it becomes more secure. It really cannot create any unwanted failure. Another feature is that it is called the software isolated process. Here these applications are encapsulated for further isolation, so that one application really cannot impact the other. One application cannot really, if the application crashes, then it can never ever impact the whole system, which is why such kind of abstractions are designed. Which is why, in fact, this kernel calls only process values. That's there. If the kernel call only accepts values, then it is not possible to really have any side effects, meaning that a call basically creates some effects which are beyond the scope of a particular method, which is more global. So essentially, this global impact is almost zero if the client calls are, if the kernel calls are essentially through value-based mechanism. So because imps are very, very limited. So let's look at microkernel and its relationship with other patterns. For example, microkernel, how is it related to broker pattern? Broker is essentially, in terms of coupling, broker makes it decentralized, whereas microkernel is more tightly coupled. If we look at client communication spec, in broker pattern, clients typically communicate via the message passing. Here, microkernel uses the ARAP strategy so that the client really do not call the service directly. How is microkernel related to layered architecture? Basically, microkernel and layer are they occur together. Microkernel is basically an use or an example of a layered architecture. Each layer, in the case of microkernel, is a virtual machine. The lowest layer is essentially the internal server, and the topmost layer. What are the pros and cons of microkernel? Benefits are it's portable, it is flexible, and it is extensible. Separation of policies and mechanisms, and it is easy to ensure that the security, as everything else can run user mode, and only microkernel runs in the privilege mode. And as I said in the example of Microsoft Singularity OS, they are really partitioning the user space, even they are partitioning the application space, so that one application really does not impact the other, so it becomes more fault tolerant. It is definitely scalable, it is more reliable because it is fault tolerant, and it is more transparent. What are the liabilities? Certainly, microkernel, from the performance point of view, it is worse compared to a monolithic kernel, because interactions are primarily through IPC, interprocess communication. There are internal, external servers, they all exist as a separate process. This is certainly more complex to design and implement compared to a monolithic kernel. Let's look at different uses. Amoeba operating system is a prototype that is built purely based on this microkernel. Chorus is another OS which is built based on microkernel. Windows NT, it uses some basic version of microkernel. Symbian operating system, which was used by Nokia for their phone, is again based on microkernel. iOS, which is based on Darwin, it is basically a microkernel architecture. iOS is the operating system that's used in Apple phones. So at the end of this lecture, I hope you would be able to, more intrigued, more interested to find out at least 2 popular uses of microkernel and document them. What are the other different uses of microkernel? Look at this particular conceptual architecture of the Linux kernel if you're interested to know more about how Linux kernel is built. Thank you very much for listening.